Hey guys, in this video we're going to solve some more trig equations, but specifically ones that have horizontal stretches or shrinks. We just have 3 examples to get through, but the solving process is going to be kind of in-depth. So let's get started. When we started solving trig equations, one of the first things we did was we thought about it graphically. So I want to start in the same spot. With example 14, it says cosine of x over 2 equals the square root of 2 over 2. And we're used to thinking of this as some kind of angle on the unit circle, and then this would be like the side lengths of some triangle. But let's think about the actual shape of the cosine graph. So remember, cosine looks like this, and think about x over 2 as being like a horizontal stretch. And that's because you got to remember that the inside of the function always works the opposite of what you'd think. You'd think that dividing by 2 would make it smaller, but it's actually going to horizontally stretch it out. And this 2x over here, this would actually be a horizontal shrink. So we have our cosine graph, and we stretched it out by 2. Let's also graph y equals the square root of 2 over 2. And you can see that the horizontal line intersected the original cosine graph at 2 spots, but our new horizontally stretched graph only intersects it once. And of course I'm talking only about the range from 0 to 2 pi because that's what the directions asked. So just to get kind of an idea of this problem, it's going to seem like we should have 2 solutions, but we actually should only get 1 solution in the end. So let's try solving this thing now. We've got cosine of x over 2 and it equals the square root of 2 over 2, and I recognize this value from my 45, 45, 90 triangle. So I'm thinking on the unit circle where I have positive cosine values because this value is positive, and if you remember the ASTC thing, cosine is positive in the first and the fourth quadrants. So there's 2 angles that I could draw. This first angle is pi over 4, and then this other angle, it's tempting to just go down and say it's negative pi over 4, but remember we got to answer between 0 and 2 pi. So it's got to be a positive number, and that's why I'm going to go all the way around the unit circle until we get to the angle this way, and call it, well, let's see. If we went all the way around the unit circle, that would be 2 pi, which would be like 8 pi over 4, but this is 1 less, so it's going to be 7 pi over 4. And there, it looks like we have 2 solutions. If we go back to the equation, because I kind of jumped into this really quick, we're kind of just ignoring this x over 2, and we're just kind of like thinking of it as theta. So it's kind of like it's saying cosine of theta equals the square root of 2 over 2, and we just figured out that the 2 values for theta are 7 pi over 4 and pi over 4. But we're not solving for theta, we're solving for x over 2. So I'm just going to replace this theta with x over 2, and then equals pi over 4. And then over here the same thing, x over 2 equals 7 pi over 4. And then we just have 1 step left basically to solve these equations. We have x over 2 and I want to solve for x, so to get rid of the 2 I'll just multiply both sides by 2. That'll cancel out over here, and then x equals, okay, so pi over 4 times 2, I can simplify the 2 and the 4, this will just become a 2 down there, so this is pi over 2. Cool, so there's our first solution, and then over here let's do the same thing, so multiply by 2 on both sides, and then we get x equals, this would be 7 pi over 2, because again the 4 and the 2 will cancel and that just becomes a 2 there. So we got our 2 solutions, just like I said we would, but the problem is that the 7 pi over 2 angle, if we look back at the unit circle, well, okay, so 1 pi over 2 is up here, and then 2 pi over 2, 3, 4, 5, 6, 7 is way down there. So I've already went outside of the 0 to 2 pi range. So we just ignore this one. It's basically like it's just an extraneous solution. So the only real solution we care about in this range is pi over 2. Moving on to 15, there's a few main differences I want to point out. First of all, we have sine instead of cosine, so that's going to be like y values instead of x values. Second of all, and this will make the biggest difference, we have 2x inside the sine function instead of like x over 2. So this is actually a horizontal shrink, we said, instead of a stretch. And the value it's set equal to is negative square root of 3 over 2, so that comes from our 30, 60, 90 triangle. But before we get into solving this, I want us to think about it visually again. So we'll graph sine of x, and then we'll shrink it because this is sine of 2x, so we'll shrink it down. And then we'll graph the horizontal line y equals the negative square root of 3 over 2. And now that we're shrinking this graph down, you can see how it's crossing the horizontal line more times than it originally did. The original graph only crossed twice, but once we shrink it, it actually crosses 4 times. Which makes sense because this 2 is shrinking the period in half, so it should cross twice as many times. So here's the big takeaway. Anytime you have a trig equation with a b value in here that's bigger than 1, which is horizontally shrinking it, you need to take some extra steps when you're solving it. So here's what that looks like. It starts out the same way it did before. So we're going to think about on the unit circle where we have these sine values. They're negative square root of 3 over 2. So it's going to be negative y values. That means like down here or down here. And I drew them as tall triangles because I remember that the sine is the y value and this is the big value on the triangle. So the height of these triangles is negative square root of 3 over 2, which means that these are the long sides, which means that these are the big angles. So I know they're pi over 3 type of angles. let's see, this first one would be 1, 2, 3 pi over 3 plus 1 more. So the first one is 4 pi over 3. And then the second one would be 1, 2, 3, 4, 5, and then all the way around would be 6, so 1 less is 5 pi over 3. So it kind of feels like we solved it already, but remember we got to come back over here and realize that we were only solving this for 2x. So what we just figured out is that 2x equals 4 pi over 3, and 2x equals 5 pi over 3. But here's the big step that's different. If I just divide these by 2, I'm just going to get two solutions. I get one over here, x equals something, I get one over here, x equals something. But remember, we wanted 4 solutions, and those extra 2 solutions came from originally they were outside of the range of 0 to 2 pi. But then when we shrunk the graph in, they shrunk into the range from 0 to 2 pi. So it's like we want to think of those angles as being outside of one time around the unit circle. So if you thought about going multiple times around the unit circle, so here's once, and then we could go around the unit circle again and get to the same angle down here. It'd be a different coterminal value, right? Because this one was 4 pi over 3, but if I went one more time around the unit circle, that'd be adding 2 pi to it. So that'd be like saying 4 pi over 3 plus 2 pi. And if I want to add these two together, I need common denominators, so I'll put this over 3 and make this a 6. So 4 pi over 3 plus 6 pi over 3 would be 10 pi over 3. Now if I take this 10 pi over 3 over here and kind of do the same thing, if I said 2x equals 10 pi over 3, so I'm just adding to my list of possible solutions or equations to solve, right? Because then I could solve this, I would divide both sides by 2, and just real quick, if you divided this by 2, you'd get 5 pi over 3, and that's back within that range from 0 to 2 pi. So since we're dividing by 2 in our last step of solving these things, that kind of means that we have to look in twice as big of a range. So instead of going from 0 to 2 pi, I'm thinking about 0 to 4 pi. So let's do that same thing. We just went one extra time around the circle with this triangle on the left. Let's do the same thing with this triangle on the right. Let's go one extra time around the unit circle. Remember, this angle was originally 5 pi over 3, but we're going to add another 2 pi to that and get all the way back there again. So if I take 5 pi over 3 and add 2 pi to that, remember to add fractions we need common denominators, so I'll change this to 6 pi over 3, and then add those together and you get 11 pi over 3. Again, that seems like it's outside of the range from 0 to 2 pi, but if I go back up here and say 2x equals what I just said, so 11 pi over 3, our last step is we'd have to divide this by 2 on both sides. So 11 pi over 3, if I divide that by 2, well, 11 isn't divisible by 2, so I can't simplify it, but if I multiply this by 1/2, that's the same as dividing by 2, this is going to turn into 11 pi over 6. And that is within 0 to 2 pi, because 2 pi would be 12 pi over 6, so we are within that range. All right, so this got a little bit messy here, but remember that these 4 equations here are like the beginning steps of solving, and then we have to divide all those by 2, so I'll write my 4 solutions down here. Now, I'm not going to write this workout, but if we think about dividing 4 pi over 3 by 2, because we have to divide this by 2, that would be 2 pi over 3. With 5 pi over 3, if I divide that by 2, we have the same problem we had down here. I can't really divide 5 by 2, but I could multiply this by 1/2, and that would give me 5 pi over 6. If I divide 10 pi over 3 by 2, that would be 5 pi over 3. And we already did this one. If I take 11 pi over 3 and divide it by 2, or in other words, multiply it by 1/2, we get 11 pi over 6. So there's our 4 solutions to this trig equation. Let's try out 16, and that'll be it for this video. This problem is similar to the last one in the fact that we have 2x on the inside. So remember, we're not going to be looking in the range from 0 to 2 pi. We're actually going to be thinking about the range from 0 to 4 pi, because all of our solutions are going to be shrunk back down by 2 in the final step, because we'll have to divide everything by 2. However, this equation also has sign squared in it. The fact that the trig equation is squared is going to throw another step into this problem. At some point in the problem, we'll have to take the square root of both sides to get rid of the squared, and that will throw a plus or minus into the problem. So let's just get started right away without graphing this one. Let's just jump into solving this one without graphing it first. Now, there's a lot of 2's going on in this problem. The 2 on the inside of the trig function is stuck in there, because it's stuck inside the trig function. But this 2 on the outside would be easy to get rid of if we just divide both sides by 2. We would have sine squared of 2x. I'm just going to write parentheses around that just to keep it organized. And then on this side is 1/2. So we got closer. Now we have to get rid of the squared. So like I said, we'll take the square root of both sides. So we'll have sine of 2x. And then over here we've got the square root of 1 on top, which is just 1. And the square root of 2 on bottom can't be simplified or anything, so I'll just leave that as the square root of 2. But the fact that we took the square root means I've got to put a plus or minus in front. If you're not used to seeing 1 over the square root of 2, that's because you need to rationalize the denominator. And this is what I'm used to seeing, so I'm going to do that real quick. We would get plus or minus and square root of 2 on top, and then on bottom square root of 2 times the square root of 2 is just 2. So this might be the value that you're more used to seeing. So then we can jump over to the unit circle and think about where we have sign values that are positive or negative square root of 2 over 2. Remember, this comes from our 45, 45, 90 triangles. But it doesn't matter if it's positive or negative sign values. So positive sign values would happen up here, 45, 45, 90 triangle. We'll draw another one over here with another positive sign value. But we also have negative sign values, so we want these triangles on the bottom. In the previous problems, our unit circle drawings just had 2 angles drawn on them. In this case, we actually have 4 angles that we had to draw out. And looking ahead a little bit, we have this 2x inside. That means that our last step is going to be dividing by 2. Remember, when we shrink the graph down, that creates more solutions. So not only are we drawing 4 angles on the unit circle, we're going to have to shrink all of our solutions down by 2, so there will actually be 8 solutions. So I'll just quickly label what we see here first. We've got pi over 4, this one is 3 pi over 4, this is 5 pi over 4, and the last one is 1 less than 8 pi over 4, so it's 7 pi over 4. But I'm looking for 8 total angles. So before we start writing things down, let me just kind of explain where I'm coming from here. We've got pi over 4 as a solution, but if I first went all the way around the unit circle once to 2 pi, and then went to pi over 4 after that, let's see, that would be 2 pi plus pi over 4. And if I want to add these together, I need common denominators, so I'll actually think of this as 8 pi over 4. And then if you add this up, you'd get 9 pi over 4. Now, 9 pi over 4 isn't within that range from 0 to 2 pi, but it is within the range from 0 to 4 pi. And in our last step, when we say 2x equals 9 pi over 4, when I divide both sides by 2, I get x equals 9 pi over 8, and this is within the range from 0 to 2 pi. It's actually just a little bit more than pi. So I just wanted to kind of quickly walk you through what we're going to be doing here, but let's actually go through the work of writing out our solutions. So I'll take the 2x from the problem and say 2x equals, and let's just go around and start with these 4 solutions first. So we've got pi over 4 was our first one, and then 2x equals 3 pi over 4, and then 2x equals 5 pi over 4, and 2x equals 7 pi over 4. And when I divide these all by 2 to solve for x, dividing by 2 is really just like multiplying by 1/2. So this will change it into x equals pi over 8. But that was just the first trip around the unit circle. Now we have to keep going around. So this first one we said that was 9 pi over 4. So I'm going to set up another row of equations to solve. I'll say 2x equals 9 pi over 4. And then we have to keep counting our way around the unit circle again. So this was 9 pi over 4, 10 pi over 4, 11 pi over 4. And then this would be 12, but we're not going there. So 11 pi over 4. And then 11, 12, 13 pi over 4. And then 13, 14, 15 pi over 4. And then I'll just quickly divide all these by 2, or in other words, multiply the right side by 1/2. Now that took us a little while, but here's our 8 solutions. We've got these 4 up here from the first time around the unit circle, and then these 4 down here from the second time around the unit circle. Although once we divide everything by 2, all of our angles, even all the way up to 15 pi over 8, is within 1 rotation around the unit circle, so between 0 and 2 pi. Because if you think of 15 pi over 8, that's really close to 16 pi over 8, and that would be 2 pi. So this is within the correct range. So a few takeaways is that solving these equations is very similar to solving the original ones we did. You start with all the same steps. The only difference is that if you have a bigger number in front of the x, like a 2, something bigger than a 1, you're going to have to multiply the range by that much, and that's how much of a range you're going to have to look for your solutions in. If this said 3x, I'd want to look in a range from 0 to 6 pi. I'd want to multiply that 2 pi by 3. Once you modify the range that you're looking in, you just go about finding your solutions on the unit circle like you normally would, and then your last step is always going to be multiplying or dividing by something in front of the x to get your actual solutions.